On behalf of the Faculty of Mathematics, I would like to welcome you to the first Dirac Memorial Lecture. Paul Dirac was Lucasian Professor of Mathematics in this university from 1932 to 1969, a period of 37 years which witnessed tremendous developments in quantum field theory and elementary particle physics. St. John's College, of which Dirac was a fellow, in collaboration with the Faculty of Mathematics, has generously established the Dirac Lectures, which will be given annually within the field of theoretical physics, and particularly the field of quantum physics, which Dirac did so much to create. We are extremely fortunate to have Professor Richard Feynman here to deliver the first Dirac Lecture. Professor Feynman is Professor of Physics and has been at California Institute of Technology since 1951. His distinctions are far too many to enumerate, but among them there is the Einstein Award of 1954, the Nobel Prize of 1965. I think he's, of course, well known to every physics undergraduate of this university and indeed the world over for the Feynman Lectures of Physics, published in 1963 and standard reading in this university. Feynman is an outstanding physicist of the present generation, renowned for his work in quantum electrodynamics, liquid helium, and the theory of beta decay, and many other areas of theoretical physics. He lists among his interests in who's who Mayan hieroglyphics, opening safes, and playing bongo drums. A man with these interests can't be all bad. It's a great honor for me to introduce Professor Richard Feynman.
When I was, does this thing work? When I was a young man, Dirac was my hero. He made a new breakthrough, a new method of doing physics, was to guess an equation. Previous to that, Maxwell got his equations, but only in an enormous mass of gear wheels and idlers and so forth in order to understand what he was doing. But Dirac had the courage to simply guess at the form of the equation and tried to interpret it afterwards. I feel very honored to, I had to accept, after all, since he was my hero all the time, and I think it's kind of wonderful to have discovered myself giving a lecture in his honor. He was the first to, as he said, wed quantum mechanics and relativity together in his relativistic equation for the electron. At first he thought that it was necessary, the spin that you had to have was necessary, and that spin was a consequence of relativity. He also invented some ideas called Zitterbewegung and other things which turned out not to be very useful in the interpretation of the equation. But after some time, with the puzzle of the negative energies he finally solved by filling them all up and making bubbles, which predicted the existence of antiparticles. And then it was realized that the idea that was necessary to wed quantum mechanics and relativity together was the existence of antiparticles. When that was added, you could do it with any spin, as Pauli and Weisskopf proved. And therefore, I want to start the other way about and start with the antiparticles and try to explain why there must be antiparticles if you try to put quantum mechanics with relativity. It also permits us to solve another problem which is very mysterious pre-relativistic times. One of the grand mysteries of the world is the Pauli exclusion principle, that when you exchange two particles, you should put in a minus sign. It's easy to demonstrate that in non-relativistic mechanics, if nature started that way, it'll be that way all the time. And so the problem would be pushed back to creation. And God knows how that was done. But with the existence of antiparticles, we make new pairs and therefore new electrons. And the mystery now is, why does the new electron that has just been made have to be antisymmetric with respect to the others and can't get into the same state as the others that are already there? And therefore, the existence of particles and antiparticles permits us to ask the question in a practical way. Suppose I make two new pairs with two electrons and I compare the amplitudes for when they annihilate directly or when they exchange before they annihilate. Why? Is there a minus sign? All these things have been solved a long time ago in a beautiful way, in fact, the simplest way, in the spirit of Dirac, with lots of symbols and operators and so on. And I'm going backwards to Maxwell's gear wheels, and I'm going to try to tell you as best I can what I think is a way of looking at these things so that they appear not so mysterious. I am adding nothing to what is known before, it's only exposition. So, here we go as to how things work, why there must be antiparticles. And ordinarily in quantum mechanics, if you have a certain disturbance on a particle which starts in a certain state phi naught, then it'll be changed, the state will be changed, and the amplitude that it ends up in a state chi is, as you all know, the projection of chi into A phi. There's a better Bra and Ket notation for that. We'll suppose that's true when we go to relativistic quantum mechanics too. Now suppose there are two disturbances, one at a time t1, A, and another at a later time, B, at time t2. And we would like to know what the amplitude is to restore the original state phi 0. The amplitude that we go from phi 0 to phi 0 is 1, the direct amplitude. And I'm doing this by perturbation theory. The next thing is the lowest order, in which first A goes into some intermediate state n, which lasts for a little time with the usual exponential. And then the intermediate state n is put into phi 0 by the operation B. This is the form in which two successive operations appear in quantum mechanics. Now, if A and B are local, that is, if they only exist in small area of space and time, they're not very widespread. We're going to make some simplifications. The way I'm going to do is first do very simple examples and then maybe talk a little bit more generally. I hope you understand the simple examples, because if you do, you'll understand all the generalities right away. At least that's the way I understand things. At any rate, one finds a term, the one plus the other term. In this case, suppose that the intermediate states are free particles of momentum p. And if they have momentum p, they'll have an energy given by their relativistic formula, which is the positive square root of p squared plus m squared. And these are the de Broglie waves which are rushing from point 1 to point 2 with momentum p and energy E. And we're going to suppose something. All the energies are positive. If the energies were negative, we know that we would solve all our problems, wouldn't we? We could keep dumping things into this pit of negative energy and get the extra energy out and run the world. But we know we can't do that, so we're going to suppose that all the energies in intermediate states are positive. Now here's a surprise. If we put together these waves with some amplitude that's any function of p whatsoever, this amplitude to get from 1 to 2 is not, and in fact it cannot be, 0 when 2 is outside of the light cone of 1. And that's a shock to anybody that doesn't know that if you started a series of waves out, they can't be confined in the light cone if the energies are always positive. Now this is a very important thing, and it therefore must be the result of some sort of theorem. And so I made up a mathematical theorem, the proof of which I don't know, but I'm sure it's right in this application. That is, if we put together a function only with positive frequencies, defined this way, the integral only over positive omega, with any weights whatsoever, to produce a function of f of t, then that function cannot be zero for a finite interval of time. You see, ordinarily you're a little bit surprised there, because you know that you can take a piecewise function at zero over a range in Fourier and analyze it, but then you'll get both positive and negative frequencies, and I'm insisting there only be positive frequencies. I got half as much data to work with, and I have two functions, the real part and the imaginary part of f, both be zero. Now, it may be that some clever mathematician can cook up some way that could almost happen with some kind of a e to the 1 over x or some terror, but I want it to be zero over an interval of time, you see, inside the light cone. And then if I change x, which changes all the phases and everything else is still zero, I don't think you can make it work zero outside the light cone. So the point is, it's definitely so that this function cannot be zero outside the light cone. In other words, there's an amplitude for particles apparently to propagate faster than the speed of light, and no arrangement of superposition can get around that. Therefore, if time t2 is later than t1, we have an amplitude to have a connection like this in which a particle goes across faster than the speed of light. But because of the principles of relativistic invariance, there are axes. If these are separated by a space-like interval, there's a speed at which time t2